Hello, our project deals with improving post-occlusion surge. The team consists of Vincent Nguyen, design leader and records keeper, Jack Loud, MATLAB programmer and materials expert, Nikita Lay, research leader and presentation expert, Sergey Palguev, team leader and organization expert. Last but not least, Javier Sanguinetti, LabVIEW programmer and MIDAC expert. Our mentor from Abbott Medical Optics is James Staggs. The first task our team completed was meeting with Mr. James Staggs. Mr. Staggs is currently a senior engineer at Abbott. He informed us about the basics of phacoemulsification and some of the current problems. After a few meetings, we decided to do more research on phacoemulsification, and here are the highlights of our findings.
The eye is a complex organ that consists of many parts working together to capture and process light information. The lens is a clear and flexible part of the eye that acts like a magnifying glass and helps us focus fine images. Cataracts are the clouding of the eye lenses, which occur through the aging process. They can be formed through UV light exposure or insoluble protein buildup over time. Cataracts affect over half of Americans by the time they reach the age 80. Cataracts can cause blurry or double vision, the appearance of faded colors, and in the most extreme cases, blindness. The leading treatment for cataracts is a procedure known as phacoemulsification surgery, a lens removal procedure that replaces the lens with an artificial lens. First, an incision is made in the cornea. Fluids are injected into the incision to support the surrounding structure. Then the top of the lens capsule is removed to gain access to the cataract. Using an ultrasonic tip, the operating surgeon then uses vibration waves to cut the lens, fragmenting and emulsifying the clouded lens particles. The smaller pieces are removed, and in its place, the intraocular lens is put there. A potential problem with phacoemulsification surgery is a phenomenon known as post-occlusion surge. Post-occlusion surge occurs when the aspirating tip becomes occluded with fragmented materials. When the tip becomes occluded, the vacuum level in the tubing rises until it reaches a maximum level. As soon as the occlusion breaks, fluid will rush into the aspirating tip to satisfy the high vacuum. The loss of fluid creates a negative pressure in the anterior chamber of the eye, potentially causing a chamber collapse and vascular damage.
So now that we have some knowledge of our project, we worked on several designs. Here's a summary of what we worked on.
The technologies currently on the market are centered around changing the phaco tip for better efficiency. This involves various phaco tip motions, which include torsional, transverse, lateral, longitudinal, and various combinations of these motions. Also, complicated manufacturing techniques of phaco tips produce beveled tips of various angles, curved phaco handpieces, and other variations in design. All of these changes to the phaco tip increase cost of the system, development of the software to control the complicated parameters of the tip, and lengthen training for the system, as proper handling must be maintained during the procedure to avoid unnecessary injury. Our design focuses on the tubing used by the phacoemulsification machine. It is well known that stiffer tubing will decrease surge through the system. We hope that by exploring different materials with varied thicknesses and properties, we can find one that will provide the best performance in decreasing post-occlusion surge. The machine we will be working on is the Abbott WhiteStar Signature phacoemulsification system. This system is the most advanced in the industry and is equipped with a multifunctional foot pedal, an easy-to-use touchscreen, and advanced software to help the surgeon perform the surgery better. For our experiment, we will set the bottle height to 75 centimeters as commonly used in the surgery room. We will vary the pressure from 100 millimeters of mercury to 300 and then to 500 millimeters of mercury. Of the advanced vacuum system in the WhiteStar, which contains both venturi and peristaltic pumps, we will focus strictly on the peristaltic pump due to its physical properties, which help us monitor post-occlusion surge better with the sensor. For our experimental design, we connect the aspiration line to the T-valve, we connect the irrigation line to the other end, and then the T-valve is connected to the pressure sensor. When the T-valve is open, fluid is free to flow through the system. To simulate the occlusion, we close the T-valve to the irrigation line. Vacuum builds up in the aspiration line, which is detected by our pressure sensor. Opening the T-valve acts as a post-occlusion surge. Vacuum is released from the aspiration line, and the sensor detects variation in flow due to the expansion and contraction of the tubing. The vacuum is applied by pressing the foot pedal attached to the White Star system. When we want to record the data, we connect the pressure sensor to the MIDAC and simulate multiple occlusion surges for each material that we test.
Here is our decision matrix. A couple parts to focus on are that both PVC and silicone fit our specifications. Several other plastics were considered, such as polycarbonate and polyethylene. However, these plastics have inferior tensile strengths, which relates to the stiffness of the material. Lastly, a metallic tube would be ideal, except that metals are not flexible, which makes it hard on the surgeon. So, we decided to focus on different types of PVC and silicone tubing with varying thicknesses and tensile strengths. Now that we have a better idea of where our project is headed, we decided to incorporate some LabVIEW programming. Here is the process of how our program came about.
For the data acquisition part of our project, we used LabVIEW and the National Instruments MIDAC to connect to the pressure probe at AMO and gather data. Really briefly, I'll be going over the data collection VI and its block diagram. This first part of the block diagram starts the data collection task. Then we have some parameters, plus or minus 1 volt. We are sampling at 1000 Hz, and we're taking all those samples. When we have 100 of those samples, we can start this loop to start showing the data on the graphs. The data is being read and shown. The bottom graph is the raw signal. The data is also being integrated on the top left, which I'll explain in a second. The data is then being written into a TDMS file, which then can be opened in Excel using a plugin, and I'll show that a little bit later. The reason we are integrating the data is because at AMO, the pressure probe does not give out actual pressure readings, but rather changes in pressure. So to get the actual pressure readout, we must integrate the signal. I'm going to plug this into my iPhone real quick so you can see what the peaks look like and what the actual, well, it's going to show voltage, but not actual pressure. But you can see the peak going on the bottom, and it's integrated on the top, and then being removed, and then on again. So one issue that we ran into, and it's not really a huge deal, but you can see the MIDAC is not plugged in to anything right now. This is just noise, which we also experienced during our tests. When you integrate the noise, for some reason it's prominently negative. So one way to not ruin our data was to stop the VI and run it over. Once it's zeroed out, it doesn't change too fast, so we can run our test really briefly and then stop it and run the next one. The TDMS file looks something like this. This is just some basic header information that it prints out. And on the next tab, we have all our data points with timestamps, which Jack then later uses to analyze in MATLAB.
So, with the data acquired, we used MATLAB to help analyze. Here are some of the basics of our analysis.
For the MATLAB analysis, we converted the voltage readout to pressure. We first analyzed how varying the bottle height and vacuum pressure affected our results. After analyzing our initial data, we concluded that varying the bottle height had no effect on the behavior of the tubing and merely translated the graph along the y-axis. We then focused our attention on vacuum pressure and changing the thickness and elastic modulus of our tubing. Our goal was to minimize the number of oscillations in the pressure readout, minimize the rise time, and minimize the area underneath the maximum peak. This was approximated using right triangles from the onset of the occlusion break till the pressure had reached its final value. Initial results for both PVC and silicone showed no decrease in the amount of oscillations for all thicknesses and elastic moduli. In addition, no clear trend could be observed when varying the thickness of either material. However, varying the elastic moduli produced variations in both rise time and area under the curve. For both silicone and PVC, the material with the largest elastic modulus had both the lowest rise time and area under the curve. Between the two material, PV showed to be the least compliant, with a 9.25% reduction in rise time and a 16.2% reduction in the area under the curve.
Now, here is a timeline of the project. The team was assembled and the project was first introduced near the beginning of November. The next 3 months were spent on planning and preparing for the project. We also met with our mentor several times as he discussed what we should expect from the project. Thus, we reviewed our MATLAB fundamentals and started to learn LabVIEW. We realized it was difficult at first trying to integrate the LabVIEW to collect the data, but after working on it at Abbott, we were able to create it. Initially, we ran into problems with finding tubing that had the proper inner diameter. However, Grainger proved to be very useful since several material properties were listed on their website and several different types of tubing with the proper inner diameter were available. To wrap up the project, we have a couple of suggestions for the future. First, instead of only the pressure meter setup we had, it would be interesting to run similar tests except using some sort of eye model. Currently, we are only simulating post-occlusion surges. In an eye model, we would be able to create a more realistic simulation. Another future suggestion is testing reinforced plastic tubing. While looking for different tubing materials, reinforced tubing was an option, but there was none that was readily available in the inner diameter we needed. Most likely, the reinforced tubing could be a custom order so that it matches the proper inner diameter.